Absolutely. So thank you very much, all of you, to be back in this room. You know, I should finish my talk now, so I'm going to start it soon. And indeed, it's a great pleasure to be here to discuss a little bit about what is known and what is not known about LNR. You know, Professor Carpentieri asked me asked me to make a short presentation about that. And to start, you know, yes, and to start maybe a picture, as we are in Assisi, about Francesco, who wrote a beautiful Cantico del Fratello Sole, because the sun, you know, gives us the light and the heat and so forth. And we all know, at least all of us accept, that the sun takes this energy from the fusion of hydrogen into helium, you know. And the dream, of course, is to reproduce this nuclear fusion on Earth. This is the reason why we see so many projects about thermonuclear fusion, like ITER. And our goal in this room is to achieve cold nuclear fusion by harnessing low-energy nuclear reactions. But in fact, going from hydrogen to helium is not an easy matter. You see that there are several steps in these reactions. It's not that easy. And even in the sun, the first reaction between two protons is the slow steps. It takes millions and millions of years to fuse the protons. After that, it goes faster. In hot fusion reactors, you know, we don't look at that. We take the easiest reaction between deuterium and tritium, making helium and neutron. More difficult to obtain, so it's not even considered in the present hot fusion reactors. Deuterium plus deuterium, it gives you tritium plus a proton, or helium-3 plus a neutron. In other words, all these reactions produce neutrons. And out of reach, at least for the moment, probably for a long time, is the direct reactions between proton and protons. Cold fusion, I don't need to explain what it is in this room, you know. Jean-Paul made an introduction to that a few minutes ago. So, LNR, what it is not, you know, the experiments with deuterium gives basically no emissions of neutrons. So, and remember all these deuterium reactions involving deuteriums produce neutrons. So this is something different. It is not DD fusion as we know it in hot fusion reactors. It is something else. The term cold fusion was inappropriate at that time, and it was misleading and created a lot of confusion, you know. This is the reason why we prefer in our group to call it low energy nuclear reactions. At least for the moment, because I am sure that a new name will evolve naturally once we understand exactly what it is. Jean-Paul showed this picture already, because this is a very important one in our community, showing a relationship between energy produced by DD reactions and the quantity of helium-4 produced. Nice? Well, accordingly, most researchers now try to understand how deuterium atoms can fuse to produce helium-4 at room temperature, and to answer some questions, how the atoms can overcome the Coulomb barrier. Why the condensed object, when you fuse two deuteriums, they do not explode immediately because there is so much energy in it. And why the energy is not released as gamma rays. And soon after the beginning of these experiments came a thunderbolt in the blue sky, you know, because some experiments worked with normal hydrogen. You didn't need deuterium to make the experiment work. Remember, protons overcoming the Coulomb barrier to fuse is nearly impossible on Earth, you know. Even in the sun is difficult, so imagine here. And then come a lot of questions. Is it still worth to look for neutrons as a proof of reactions? And where do the protons end up? The protons, they make reactions. What kind of reactions? So, most probably, the lattice we use to dissolve the hydrogen plays a central role, you know. And many theories are elaborated accordingly. But these theories must be able to explain all the observed phenomena, you know, not just one phenomena, but all of them. Because there are many phenomena to explain. For example, the production of tritium from deuterium. You see here an autoradiograph of a titanium sample obtained in Bombay Atomic Research Center in India. And you see these titanium crystals delineated by emissions from tritium. Tritium, you can get also that from light water. Ask Guido Parchi, who showed recently an interesting experiments proving the production of tritium starting with light water. Jean-Paul told about Claytor as well. Huh? In terms of phenomena, we see also occurrence of hotspots. This is a movie, but the movie is not in this computer. So, but in these experiments, you made a co-deposition of palladium in heavy water, and you see at the back a lot of hotspots. Many flashes, you know, showing local reactions. It works. I was not expecting that, you know. Well, okay, fine. And during such reactions, you see also hotspots, you know, with some metal fused in craters, a few microns in diameter, a lot of them, showing that when you get some reactions, it gets very hot locally. You get better activity in nanostructures, you know, especially when these crystals contain different metals of different sizes, like nickel and copper, most probably because they have different diameters, and there is a mismatch between these atoms with small gaps between them. I don't know, but apparently it helps. And because of that, the Japanese obtain such results, you know, obtaining excess heat at different temperatures with nanopowders placed in hydrogen. And by the way, nothing in deuterium. Strange. More recently, in this project, Jean-Paul Biberian and at Vegatech, they saw also excess heat in materials produced from hydrotalcite, you know, hydrotalcite. Also, Francesco Celani in Frascati, they are producing some heat with Constantan alloys, nickel copper alloy, thanks to pulse discharges of electricity in a deuterium gas or hydrogen. Both. There was a conference in California a few weeks ago, and where Brillouin Energy was demonstrating a small reactor with their system, working again with multi-layer of nickel on a metallic rod in hydrogen, triggered with high-frequency pulses. And this is a picture I took of their computer. And you see that the heating and electrical supply was consuming 235 watts of electricity to produce 260 of heat. So it seems to work. Ask Konrad Chersky, who was also there. Not only electrical pulses can produce heat, but also hydrogen diffusion through appropriate materials. This is a picture from a clean planet. They have different multi-layered materials loaded with hydrogen, and when you pump out the hydrogen, you see some excess heat that decreases along many days, 40 days, 80 days, 100 days. It goes slowly down, but you still have some excess heat produced in this case. This is how they make now 1 kilowatt prototypes thanks to such reactions. They see also something different, also something else to explain. It burst. You have these multi-layer samples of nickel and copper, you load it with hydrogen, good. You pump the hydrogen and you see some excess heat. But it's not a flat curve. At times you get bursts like that, and it decays within minutes, and it starts again and decays slowly. What is very strange is the very fast rise, and even stranger for me is the slow decay. So it means that this heat burst is not just a hotspot popping up, but something much more complicated, Others at DARPA in USA, they measured radio frequency anomalies, after a few minutes after the start of electrolysis, They observe radio frequency signals, quite strange. A lot of the pictures I present are not the same as Jean-Paul showed. You show a lot of material, I show something else about the same kind of phenomena. Just to tell you that both of us, we picked up a few slides, because we have a limited time, but there is a lot of materials to be discussed in such cases. Again, transmutations, Iwamura. I saw the badge of Iwamura on the table, so Yasuhiro Iwamura should be there tomorrow, maybe. Some time ago, he measured some transmutation by deuterium permeation through samples. Also, more recently, Ubaldo Mastromateo, Jean-Paul Biberian, and Barrows in USA, all of them tried to put some laser beam on a palladium sheet in hydrogen gas, and they observe some transmutations like that. It starts with palladium, and after a few days, many days, they see something else like sodium, calcium, nickel, and things like that. Then comes the question, Eleanor, are we talking about fusion reactions? Are we talking about fission reactions? Are we talking about both? Indeed, this is the question, Another system with arc discharge in water, you have very pure carbon electrodes, and at the bottom you find carbon debris, of course, but also iron, nickel, many other things. Strange. Not present, obviously, in the original setup. Many more things to be discussed, like neutron emissions in cavitated liquids, or during the fracture of solids. Ask Alberto Carpentieri about all these experiments. it should trigger questions. Strange tracks at times on the surface. Here this is a zirconium ingot, but it could be a polycarbonate plate. You see such strange tracks, you know, like streaks, but they are not just stupid lines like this one. They have an helicoidal form. At times you see a change of directions. Very sudden, you know. You don't have a gentle turn, there is no inertia. This thing move here and move again in that direction all of a sudden, as it had no mass at all. So what is known indeed? We do have reactions. The reactions are obtained in deuterium and hydrogen. The presence of a structured metal lattice is required. Some alloys work based on palladium alloys, nickel, copper, titanium. The generation of heat is beyond any chemical, let's say, normal explanation. There is no or very few neutrons, and frankly speaking, there is a necessity for out of equilibrium conditions. You know, heating up is good, but if you have electrical pulses, diffusion, things like that, it helps. So what remains to be known? Well, we need a theoretical explanation. One theory or several, because is one single theory able to explain everything? Is there a unique mechanisms or several ones? Do we have to explain fusion and fission separately or with a common theory? And indeed, the comprehensive theory will have to explain all phenomena. But for sure, as I am on the industrial side of the project, in charge to use what you are going to invent, for sure, if we have to develop this kind of use of energy in the community, let's say in the world, we will need an acceptable theory if we want to have this energy accepted, you know. If you have a very nice thing and you can explain to people, oh, we don't know why it works, try to sell it. I don't. Towards the theoretical explanations, you know, electron screening, enhancement, I'm sure Conrad will explain much more about this. Shrunk hydrogen, I don't see Jean-Luc Payet in the room, he will be there tomorrow. Formation of ultra-dense hydrogen layers and Rydberg matters. Svein is looking at his phone. Coherent correlated states of hydrogen atom, heavy mass electrons, well, just to say that all these phenomena, all these theories have something in common. They all rely on the realm of quantum mechanics. And I just selected a few slides to illustrate the speech and nothing more. But in America again, DARPA, or the US Navy, or in other words, is developing a theoretical roadmap and explaining that maybe with a DC current you can pump deuteriums from places to places, helping in the fusion of these deuteriums. Well, interesting. The fact is that Mitchell-Schwarz, we saw a slide from Mitchell-Schwarz a few minutes ago, is doing exactly that in the nanor, you know, with some DC current flowing through nanopowders loaded with deuterium. And there is apparently an effect of this current, DC current excitation. Jean-Paul told us about the possibility to have correlated states with phonons exchange and things like that in the matrix. Some other researchers like Vladimir Vysotsky is looking at correlated states on a single atom, having all of a sudden several states and large fluctuations, maybe. Clean Planet, as I told you, is working thanks to diffusion of hydrogen through metals at high temperature. At high temperature, the hydrogen can easily diffuse through metals. It's even difficult to confine hydrogen in bottles for a long time at a high temperature because it goes away. And with a correct setup, you get some heat. Quantum mechanical effects are also required to explain, I guess, screening and resonance effects in the lattice. Conrad can talk a lot about that. There are other theories, maybe Hertzians. I don't see Bill Collis in the room, but he could talk a lot about that. Virtual neutrons. You know, we could have, as you said, Jean-Paul, maybe 100 theories listed here in this slide, so just a few ones. And to finish the speech, just the last one. Recently, there was a claim that between two layers of graphene, you can get superconductivity at room temperature. And more recently, it seems that if you have a current flowing between these two layers of graphene, you rather get creation of electrons and hole, like through a Wigner effect, mimicking the superconductivity, but, well, just to say that there is a lot of things to look at before getting a complete explanation. That's all. Thank you.
Okay, we have now time for questions.
And I have no answer. Go ahead.
Well, I'm just add a few words about these graphene layers. It is well known that in graphite you can insert between the layers alkali metals, you know, ions, sodium, potassium, lithium. And hydrogen is of number one alkali metal, but it's a molecule, so you have to break it first and then put it inside the lattice, the layers. That's why there was some work. Case used coconut shells as a support for the catalyst, and it is very possible that the palladium that's on top of the graphite, the carbon, dissociate the hydrogen, deuterium, so that they go in between the layers of the graphite. And that could be an explanation of why it worked. That's all I wanted to add. That's comments.
Sorry, but in this case, it was monoatomic deuterium, hydrogen, you know, between two layers, and traveling thanks to an electrical current, you know. You have to read the publication and you will see that.
Okay.
Okay. There are some other questions, comments, and discussion contributions. So we discussed so nice different points. So
I have a question.
Here is okay.
You can speak with us.
Yeah, okay, go ahead.
Bo, you are online, yeah?
Yes, okay, thank you.
So you can
Jacques,
ask.
do you think or believe or is of the opinion that linear reactions has solidly been proven to exist in experiments? In other words, do we have any experimental results which undoubtedly prove the existence of linear?
That's a good
indication. Yeah.
I love this question because I am sure I don't have the answer. But this is an excellent question to sum up this discussion. And I see that Andras Kovacs would like to get the microphone, you know.
Yeah, there is Andras Kovac. There is a...
Yeah, I would like to just comment to Bo's question that in Jacques, in your presentation, you showed this laser illuminated palladium foil experiments that has been now 3 times produced, as I understand, with the same results. So that's apparently a replicable experiment, because so far we did not know of anybody who tried and did not produce it.
Thank you very much indeed. The fact that it is replicated is very important. Jean-Paul did that experiment, so I would like him to comment on that, because I can just repeat that what you told me, that this is not that easy. You get a few spots, you know, you have to find out these spots and to analyze right on these spots, and elsewhere there is nothing to see. So what do you think about that? I guess this is an easy experiment and all of us should try to replicate it.
Okay, about the question from Jacques, the use of hydrogen and deuterium, it works. I have to clarify that using our Constantan copper nickel alloy, in the old experiments, we started with hydrogen, and after sometimes we moved and got some chassis. When we moved to deuterium, we got negative heat, very, very strange. So we cannot understand. It was under the calibration. So negative in a way, cooling. So we stopped to explore the deuterium. This year, for a lot of very complicated situation, we decide to explore again such very strange phenomena. And at the beginning, means 1-2 days, we have again almost 0 chassis heat or negative. But after 1 week of operation, with the deuterium, we have some anomalous heat, even larger than hydrogen. So we decide after 1-2 weeks, 2 days to stop experiment, clean as much as possible the wire by vacuum, high temperature, and so on, and we restart again after, and we put the system for 6 days at a very high temperature, and start again with the deuterium, and it was the best experiment we got in static condition. So maybe the long time conditioning has some rule, and usually the experimentalist after 1 day, 2 days stop exploring because I have nothing, why waste time? So maybe long time effort, several did consider as to be a parameter. So I just suggest this point.
Maybe I can say something what is maybe more general. So we report about different effects, more or less power emitted, produced. But the problem is within our project, just we want to go to the next part of this meeting. For this project, something is much more important. We should look for some correlations, for some explanations of the effects we have seen. So we report once again different things. Yeah, they are really very interesting. But what is most important to understand the effects, to go further, to make a progress. So we will be speaking about the progress. This very nice place to summarize the knowledge we have. But within our project, we should present the progress we made last year. Okay, so we cannot speak over 30 years. There were so many nice experiments, and some of them work, and some of them not. Yeah, so we should compare our results with the previous year. And there is something what is much more important. Okay, so coming back to your presentation, Jacques, this just what you said, Francesca, this illustration for that how difficult, how complicated are the effects we want to measure, we want to control and use for energy production. So it is not so easy. Yeah, we know about it. Nevertheless, we should ask ourselves, yeah, what kind of correlation, what kind of observables are most important to go further, to understand it. Yeah, and for instance, as I heard here, we see something like this, that that in palladium deuterons work very nice, but protons not so much. And nickel, you said there were, till now at least, the people said there is a system for protons, but not for deuterons. But you have measured now that deuterons work as well. Yeah. Yeah, this, of course, yeah. Okay, yeah, but you have this multi-layer system, nickel, copper. It is something what is comparable, a little bit, at least. Okay, so we are looking still for some common features that can be explained. That is not so nice state, let's say, if we are discuss about our project. We will come back. So this is the question to you, yeah, once again. What kind of correlations or experimental correlation you would see in all these effects, experiments performed before? I don't know. There was also a question to Jean-Paul, yeah, because he is also so experienced. This is not so easy. We measure 30 years, over 30 years, and see very nice effects. Yeah.
You know, if we think about these experiments with laser in hydrogen and palladium, it would be nice to try other metals and to find out if it is efficient or not. And so it takes a lot of work, because again, this experiments is fascinating, but you get a few spots, you know. So you need many setups to have more spots to look at to find out what you have. And also, what I would like to do is, as about this one, influence of electrical current, and also maybe diffusion. If you consider this kind of experiment, you have a plate, a sheet of a multi-layered material, and the hydrogen is going through. Nice. It means that you get something behind. Good. And analyze what is the difference between the gas in front and the gas behind. If you find something or not different, you know, it would be an indication.
So maybe the answer is that we should start to measure very simple systems. This is just a usual approach in physics. You should simplify the systems and look for very simple effects or simple phenomena to say something.
Because in this case, imagine this is a sheet of multi-layered material. You put hydrogen or deuterium here. You recover your hydrogen here. You pump it again, back, many times, you know, and to see if there is a build-up of something else different. Easy?
The question is, we will have time for that, you know. If you want to measure all the things within our project, you know, transportations and all the things, this is really difficult, yeah. So there are many interesting effects.
This is the point. We have to select. This is gambling, you know, in such a project. We have to select a few things and to take as we say in France, you know, you take the duck and you turn the head until it's dead, you know. You have to... You select one and you do it, you know. One experiment and you try to get as much information as possible from that experiment. If all of us, we do 10 or 20 experiments, you know, we discover that there are much more things to explain than what I listed here. And
okay, so what do you think about discharge experiments? Because, you know, in our project we have accelerator experiments. Yeah, on the other hand, it is high energy. We have gas loading experiments at roughly room temperature with 1,000 degrees, but nevertheless, there's still very low temperature. And discharge experiments could be something just between. You can change the voltage, you know, you can change the pressure, and then you see something just between accelerator and gas loading. So, and there are some very nice examples. I don't know, we will present here during the workshop some results presented in the ICCF 24. Yeah, there is a, I don't know, I don't remember the name of this PhD student that presented this charge experiment using the CR39 foil to measure charged particles, and the results are very, very nice, and there are in agreement with the previous results obtained in different other experiments. Maybe there is a solution. What do you think about it?
Concerning discharge experiments, you know, I have to come back to a political situation. Because discharge experiments, this is largely, heavily, let's say, investigated in Russia. And they make a lot of experiments and they see many, many things. I guess that Andras could confirm that, especially in dusty plasma. Plasma, which is not a pure gas, but you manage to have a lot of dust in it, and you put discharges, and you measure again what you get. And they get heat, they get transmutations, they get many things difficult to believe outside of Russia, but it's probably worth to, if not to collaborate with them, at least to try to do something like that.
I think the systems are very easy. We don't need to collaborate.
I mean, I think Hungary is not part of Russia. It's no more. But George Eggerly has done this experiment with dusty plasmas. And I've done it myself, and I've seen the transmutation, but he can give more details because he's the one that started the whole thing.
Yes, actually, in my opinion, the dusty plasma makes the whole universe running, because sun is attracting lots of dust, interstellar dust, and certainly there are indirect proof that this is running our sun and all the stars, simply because there is an 11-year cycle, for example, with the heat output of the sun and the solar cycles and sunspots and so on. And each 11th year, the major planets are aligned, and they are disturbing the distribution of this dust cloud around the sun. However, we were able to make quite sophisticated dusty plasma experiment with microwaves. And in my lecture, I shall show you some pictures. And I'm doing actually right now discharge experiments, and we are producing electric energy out of it. And we went back 150 years to Tesla and 100 years to Moray for these old experiments. And I found about 15 completely forgotten discoveries, patents. and not only patents, but just discoveries about these arc discharges and other kind of discharges which are producing electrical energy. And we were able to present at ICCF 24 a small device, pocket size. We can put it into our pocket, walk, and it produces electrical energy. So I think this is really worthy of consideration experimentally. I will show you some slides.
Oh yes, I look at your presentation in ICCF 24. It's really fascinating. But in this specific case of this small device, you don't use a dusty plasma.
No, it's not dusty. It is just spark discharge.
Absolutely, absolutely.
It's a different.
Yes.
From time to time, I change my field, but it is always LNR.
Is it always LNR? Are you so sure about it?
Jean-Paul found carbon soot traces on the face of this cathode, and there is no carbon inside the original system. Somehow transmutation takes place, which I don't like personally, but it happens.
And you observed the same buildup of carbon?
Yes, over and over. We really don't like it, but it crops up always.
And Jean-Paul reproduced exactly the same, saw exactly the same appearance of carbon.
I mean, George gave me the sample, and I did the analysis on the electron microscope. That's all. I didn't do that experiment. What I did was a dusty plasma experiment with microwaves. And definitely there was transmutation of carbon into all kind of elements, yes. So it's alchemy.
Okay, we are just, we should think about another part of our meeting. Yeah, so we can discuss the questions during the workshop, of course, and then you will see finally what is new after this 3 days, yes. Okay, and finally maybe we will have some conclusion also for us, yeah. Okay, so I think we can finish this part of the meeting, and then we can go to this formal General Assembly meeting that is necessary to start now, and only the people that are collaborating and that are parts of our project can contribute and can stay here in this lecture hall as well. You know. Okay, so you know the.
Also online will be YouTube will be stopped.
Yeah. So. Okay.
Only Zoom with internal people.
Okay. So. So the point is, we should discuss, you know, or maybe we can make a short break if you want, 5 minutes, yeah, something, yeah, because it is.